So our next presenter is Terry, who will be telling us about chasing a ghost, one fool's quest for perfection in SPMHD.
Thank you. So my name is Terrence Tricco, or Terry is fine. I'm a former PhD student of Daniel Price. I've titled my talk Chasing a Ghost, One Fool's Quest for Perfection in SPMHD. And it'll kind of become a little more clear, hopefully, as we go through this talk, exactly why I've chosen this title. So my research interests, I'm really interested in the pedantic numerical details of SPH. I'm a numericist. I like numerical methods in terms of testing them, designing them, how do they work, creating numerical methods. I love every aspect about that process. And one of my key research areas, and one of the key areas that I'm still interested in, is around smooth particle magnetohydrodynamics, so incorporating magnetic fields in the SPH framework. So I've structured my talk today sort of in two halves. The first is around a little bit of a review, I guess, in some sense, of just like what is the modern state of SPMHD and sort of how did we get here? And I think we can sort of rewind and go back to the very beginning. In 1977, there was the initial paper that introduced SPH to the world by Bob Gingold and Joe Monahan. Some of you might know Joe. And at the time, there was this unbridled optimism about performing MHD with SPH. And there's this great quote in that paper about how magnetic fields may be included without any difficulty. This was followed by decades of toil and turmoil, of trying to figure out how to actually make this reality in practice. It was because it was not necessarily so straightforward at the time. However, in some respects, Joe was right. And if you know Joe, and if you ever talk to him, when he talks about SPH, he's often right about a lot of different things. And it's sort of hindsight, it is straightforward what you need to do. There was a lot of dead ends that people took and a lot of twists and turns of how to get to the modern SPMHD that we use nowadays. But in hindsight, it is relatively straightforward. You take the induction equation for evolving B forward in time. This is just the continuum equation for how to evolve B with respect to time. And you just discretize this in a standard SVH way. That's it. This gives you some really nice properties, namely Galilean invariance, in that if there's a background velocity, it doesn't impact the quality of your result. You get the same result. So this piece is very straightforward. And there's sort of three pieces that you need to put together. One is how to evolve B forward in time, and this piece is straightforward. The second is that you have a force from your magnetic field. The force, right, you have a magnetic field and it wants to push or pull things around. Creating that force in SPMHD is also relatively straightforward. You take the Lagrangian, you take your magnetic energy as part of Lagrangian, and you solve for what the conservative equations of motion are. The exact same process you do to get the equations of motion for your hydrodynamic equations. And you can see you get three pieces, you get three terms in this set of equations. This first term here corresponds to the pressure gradient, which I hope many of you are familiar with. And then we have these two additional terms. And you can understand these terms directly in terms of the magnetic stress tensor. You can express the equations of motion using this stress tensor S here, where you have a hydrodynamic, or like a thermal pressure, isotropic pressure. You have an analogous isotropic magnetic pressure, so you have this 1/2 B squared. And then you have this extra magnetic term here, which corresponds to like a magnetic tension. So if you have two fluid elements, they're connected by a magnetic field line. It's almost as if they're connected by a string and they want to resist, you know, moving apart, and they kind of have a attractive force that wants to pull them together. There's a tension in the field line. And you see this direct one-to-one correspondence between this stress tensor and the SPMHD equations that you derive. Here is your 1/2 B squared, here's your isotropic magnetic pressure, and here is your BI, BJ term, right? Your BI and then BJ term, and which corresponds to your magnetic tension. Very straightforward. The third piece you need to put together to make all this work together is that you have to have div B equals 0, right? This just comes out of Maxwell's equations, div B equals 0. In practice, in a simulation, so like, well, in nature, like this is true, right? Div B equals 0, but is it true in a simulation? The previous two steps that we did doesn't place any constraint or any guarantee that this is true. So we have to do some extra work to guarantee this. And the problem is that, one, you want to have a zero divergence of B because that is physical. If you have a non-zero divergence of B, that means you have an unphysical field. And if it's a really large non-zero divergence of B, then that means you have a really unphysical field, and that just feels bad and might cause problems in terms of the solution you obtain. But it's a little bit farther than that as well in terms of this magnetic tension that we looked at. So we have this BI/BJ term in the stress tensor. You can expand that out to, and I'm missing here the DXJ term to expand this out. It gives you this first term here, and it gives you this second term. This second term is proportional to div B, right? So in nature, this is okay. In nature, we can add this div B term here. We can multiply this by 10. We can multiply this by 1,000,000. It doesn't matter because it's 0. Div B is 0, so it doesn't matter. And we add this in mathematically because it gives us this nice mathematical form of our stress tensor. In a simulation, div B might not be 0. So all of a sudden, it does matter that this is here, because then you have this unphysical, spurious force, which in practice acts as like an exaggerated tension. It places, it increases the tension that you experience, which in practice causes an unphysical clumping of particles. And that's a bad thing. Particles clump together, and then you start having all sorts of numerical effects from that. The fix for this is relatively straightforward in hindsight, in that all you need to do is subtract out the unphysical force. You have this term here, which is this part, which is physical, and you have this part, which is unphysical. So numerically, you just subtract that out. You just get the SPMHD equations, just discretize this, subtract it out, and your job is done. This yields a robust, numerically stable solution. The problem is that it's no longer momentum conserving. In practice, this is not really that big of a deal. And you can see that, like, if div B equals 0, then this non-conservation is basically a non-issue. And in practice, in modern SPMHD, this is really not much of an issue at all. But the question is, how do we uphold div B equals 0? Right? That's the big part we have to figure out. And this has been the big stumbling block for how to get SPMHD to its sort of modern state. And this has been one of the key contributions of my research in this area. And it's what I did a lot of work with Daniel when I was doing my PhD. We developed this divergence cleaning method for SPMHD. This is based on an earlier method by Dedner in 2002, where they add this new psi field here, and they couple this to the magnetic field. And you can see psi grows based on div B. And the idea given by this sort of cartoon example, say you have some sort of blob of divergence. If you don't do anything, it'll just be passively affected with the fluid flow. You have a hyperbolic and parabolic system equations. The hyperbolic portion spreads this out as a series of waves throughout the system. And then the parabolic part damps that away over time. And the combination of the two, using the hyperbolic part, helps enhance the rate at which the parabolic part works, and the divergence errors are damped away. Sorry. And this has given us basically a decade of rich scientific applications. SPMHD has now been used for a wide variety of things, like star formation, looking at jets from star formation, looking at the magnetic field orientation within the Milky Way galaxy, star cluster formation, molecular clouds, tidal disruption events. James Worcester talked about colliding clouds, and he's done a lot of great work looking at binary star formation and lots of applications there. People looked at more fundamental things like the magnetorotational instability, demonstrating that SPMHD can do that. Looking at the small scale dynamo and turbulence, and demonstrating that SPMHD can do that. And then people have also used this in non-astrophysical contexts, looking at basically plasma for fusion energy research, sort of plasma in a tokamak reactor. So SPMHD is in a very good place these days. And it sort of all rides on this divergence cleaning method. Has been the sort of the final key to unlock everything. As I mentioned, this divergence cleaning method was based off of an approach by Dedner in 2002. Daniel, as part of his PhD, actually investigated using this cleaning and published that in some work he did in 2004, 2005. And at the time, he found when you use this parabolic cleaning, and we have a simulation here of the average divergence of B throughout the simulation over time, and this is for the Orszag-Tang vortex. We'll take a look at that in later, but like right now, we just need to look at this solid line, which is the average div B, where there is no cleaning. So no cleaning gives you this solid line here. If you apply cleaning, most of the time you'll get basically a factor of 2 reduction. Sometimes, if your parabolic cleaning is not strong enough, you can actually end up with an increase in DIV-B, an increase in DIV-B over the no cleaning case, which increases by a factor of 2 to 3 here. So the hyperbolic cleaning is comparatively small and can in fact increase the divergence error. So how do we go from that to now all problems have been solved? Our approach was to take the perspective of energy conservation, because I want to peel the onion a little bit deeper on how we did this, because it's going to tie into our conversation about where SPMHD is going in the future. And the insight here is that we have this new cleaning field psi that's coupled to the magnetic field, and energy is transferred between the magnetic field and this field. And this energy transfer must balance. If it's imbalanced, then you've created spurious energy, and this may lead to an increase in divergence error, as Daniel found. So what we need to do is define the energy stored in the cleaning field. That's straightforward enough to do. And then make sure that the energy transfer between the magnetic and cleaning field is balanced. That is, the time change of the total energy is 0 for the magnetic field and the psi field, at least for the hyperbolic portion. When you do this and you solve for the SPMHD cleaning equations, you are imposed very specific operator choices. You must use a first order accurate method for calculating DIV-B, and this imposes a 0th order accurate method for calculating the gradient of psi, which is not intuitive. Intuitively, you'd want to use a high order method for calculating these derivatives, but to conserve energy, you have to use a lower order method specifically for the gradient of psi. And going through this process as well, we realize that the original equations by Dedner, given here, are incomplete, in that the full set of equations need to account for density variations, which are understandably important in many astrophysical contexts. And this cleaning rate CH here, which gives the rate at which those hyperbolic waves propagate outwards, that can vary over time. And you can account for that as well, and doing these things also improves the quality and performance of the method. So our constrained cleaning typically provides a 10 times reduction in divergence error and keeps the average error around the 1% level. And it's constrained in the fact that it prevents the case seen by Daniel in 2005 of you are restricted. It is impossible to increase the divergence error. You can only ever at worst, keep it the same, or most likely places reduce it, typically by a reduction about 10 times. So fixing the lesson here is that fixing energy conservation fixes the numerical method. You have to trust SPH. SPH knows best. Let SPH tell you what to do. Build your numerical equations to conserve energy, and many of the problems that you experience will be solved. So let's talk about the future of SPMHD. My future research goals are around to create a truly divergence-free SPMHD method. Divergence cleaning has unlocked many research areas, however, is an approximate method. Divergence errors are continually being introduced and then cleaned away. The steady state here is typically around the 1% error level. Ideally, we want, or at least I want, as a numericist, is a method that prevents divergence errors by construction, to get away from this sort of post-processing cleaning this, have it as a pre-step where you just prevent divergence errors from even manifesting. One approach to do exactly this is to use the Euler potentials. You can define these scalar potentials alpha and beta, and you take the gradients of those, take the cross product of them to reconstruct a magnetic field. You evolve the potentials, which is, in terms of SPMHD, they're just passively advected. Recalculate B based on the new configuration of alpha and beta, and then you just use SPMHD as normal. This works well. This works extremely well, sort of. And there was a bunch of work done in the late 2000s doing star formation, binary star formation. Apologies. Star formation, binary star formation, neutron star mergers. Sorry, but the Euler potentials do not live up to their potential. They cannot represent certain magnetic field configurations. They can represent toroidal fields or poloidal fields, but not both. And as such, they cannot create such complex fields during a simulation. So as a concrete example, simulations using Euler potentials do not see jets during protostar formation, which we do see in modern SPMHD simulations. Sorry about this. Formulating the magnetic field in terms of the vector potential seems the next most logical choice. You have this potential A, which is a vector. You take the curl of that. The divergence of the curl is 0. You are guaranteed a divergence-free magnetic field. All we need to do is evolve the vector potential, which at a very high level, run through the derivation here. You have dB dt, which is d curl A. You have a curl here. You can uncurl these things. You get dA dt with some gauge choice. Convert this to a Lagrangian derivative. Choose a suitable gauge choice here. One option is to do that, use one here that basically changes these derivatives off of A onto V, which gives you a very nice Galilean invariant SPMHD equation. Great. So in theory, all you need to do is evolve the vector potential, reconstruct the magnetic field. You have B, you could plug B into the SPMHD equations of motion. What could go wrong? And this is what Daniel did 2010. Well, it's numerically unstable. This is the Orszag-Tang vortex at a low resolution, medium resolution, high resolution. Basically, what happens is you end up with these large, like empty voids. It doesn't conserve energy. You have this exponential growth of energy, which creates these voids. As you go to higher resolution, this occurs earlier. So this vector potential formulation is highly numerically unstable. The problem is that it does not conserve energy. And we can understand this in the fact that the equations of motion were derived assuming the magnetic fields evolve according to the induction equation, which is what I showed earlier. We are not doing that. We are evolving the magnetic field using the vector potential and using a mismatched set of equations of motion. So therefore, you get numerical instability, energy grows exponentially. So the fix here, in theory, is to listen to SPH, right? Create the equations SPH wants us to create, conserve energy, all problems will be solved. Solve for the equations of motion in terms of the vector potential, right? All problems will be solved if we do that. And this is what Daniel did in 2010. He went through this process, and you end up with basically 3 terms, or at least there's 3 important terms. In that, I'm neglecting, I'm assuming there's a constant smoothing length. You have other terms related to varying smoothing length that I'm ignoring for this talk. But this first term here, here's your hydrodynamic pressure, and you have a negative magnetic pressure. Right, you have an isotropic magnetic pressure that wants to pull things together. You have a second term here, which is problematic in the sense that you have this second derivative of the kernel, which is a very noisy estimate most times, and that's a bit of a problem. And then you have this third term here, which has J, which is the current density. And solving for these equations imposes a very inaccurate estimate for the current density. So in order to make any headway, Daniel had to address all 3 components of the force. He had to stabilize the negative pressure gradient, had to use high order kernels to get a reasonable measure of the second derivative, had to use more accurate operators for the current density. He could simulate a shock tube, but that's about it. The 2D, not even 3D Orszag-Tang vortex, we are unable to produce a stable and accurate solution using a consistent vector potential formulation. It's basically dead in the water. So Daniel concludes with some gentle caution about the vector potential, saying, perhaps the most useful aspect of this paper, apart from acting as a warning to the reader intent on similar endeavors, is the formation of the dissipative terms. And he concludes that the vector potential is not a viable approach for SPMHD. So what have I been working on the past while? I've been studying the vector potential off and on for the past few years, attempting to find any progress forward on this problem. And we had initial promise of some hope that if we change how we evolve the vector potential, this might solve some of our issues. In particular, we take the evolution equation here, and we can take this with an integral approach. integrate this over the volume. We get, here's our V cross B, or this V cross B here, plus this surface term. We can convert that to a volume integral, discretize this into our particles, and we get a different evolution equation for A. And initially, this seemed really promising. If we look at the Orszag-Tang vortex, and here we're showing our low, medium, high resolution using this integral vector potential formulation. In the bottom row, we're comparing to the standard SPMHD formulation. Everything looks great. Nothing is blown up. Even at the high resolution, everything looks great. But when you go to later times, this numerical instability still sets in. Right at a high resolution here, you can see these large low density voids, or basically empty voids appearing, and the energy does go through this exponential growth, and your simulation basically crashes at this point. So we run into the same sort of problem. So this evolving the vector potential with this integral approach helps. It helps a bit. It's still numerically unstable. We can evolve the system for longer than before, but it's still numerically unstable, and at some point, your total energy just goes exponential. Also, this form is not Galilean invariant, which is the feature that we're missing, which would be really nice. Perhaps different gauge choice might fix this, but the conclusion here is that this is still not a panacea to our problems. The second avenue I've been investigating is to address the problems with the consistent formulation of the equations of motion, with the goal of conserving energy. Right? We have these three terms here. What can we do? Like, what levers do we have to pull to try to address some of the problems here? This first term, this negative pressure, we're kind of stuck with this. In theory, the rest of the terms contain part of the isotropic pressure which balance this. That's not necessarily true in practice, but it is true in theory. This second term here, the second derivative of our kernel, this arises solely by the choice of the kernel that's used to reconstruct B. Right? B is curl A. The kernel choice used for there comes into this second derivative. So maybe there's something we can do there. This third piece comes about our choice of how A is evolved, right? And we have at least some other ideas of how we could address that. So one option for using a better second derivative kernel is to use a higher order spline. In fact, this is what Daniel had to use. He had to use at least the quintic spline to achieve any progress here. The second option is to use a different kernel, a different family of kernels. So one thing I've been testing is to use an integral approach to derivatives based on Garcia-Sens, where they define the kernel gradient as something different than just literally taking the derivative of the kernel itself, right? Which is what we normally do. We just literally take the derivative of the kernel and apply that. Here, they use the kernel directly with a bunch of stuff in front of it. So they just use a standard kernel weighting with a bunch of stuff to calculate a gradient. This is just the difference between particle positions. This C here corresponds to this tensor C, which is the inverse of this tensor, which is a summation of, again, just a regular kernel. So in theory, we can avoid a direct second derivative of the kernel by using something like this, for example, and then only having a single derivative of the kernel itself with a bunch of other stuff that maybe this might solve some problems. So this might just avoid a direct second derivative of the kernel, might very well solve the second term of the force equation, but may and probably likely will introduce more complication without providing a solution. This is work in progress. I'm still working through all the math on this and trying to test this through simulation. Time will tell on this piece. So this brings me to my summary. I want to summarize with a very positive note that modern SPMHD is robust and widely applicable, has been used to study a wide range of astrophysical problems. Resistive MHD can be included, like the ohmic, dissipation, ambipolar diffusion, Hall effect, through a lot of the work of James Worcester, and all of this is in Phantom. All of this is in Phantom, ready to be used. The foolish quest to find a truly divergence-free SPMHD continues. At least one fool is continuing to work on this. A solution remains elusive, but this is okay because the standard SPMHD works so well anyway. And I think there is some slight glimmer of hope for progress beyond our current state, but time will tell. So thank you, everybody, and I'll take any questions anybody has.
Thanks, Terry, for the interesting talk. Does anyone have any questions?
In your integral approach, I was just wondering, so when you have an MHD Riemann problem, you have these intermediate shocks through the Alfvénian waves. And is there a problem in like doing these integral methods when you have these discontinuities, or is it still like straightforward?
I think it's still straightforward. I mean, the approach we do in SPMHD regular is to add an artificial resistivity, very analogous to the artificial viscosity to capture shocks. We do this to capture discontinuities of the magnetic field. And this is something that sort of Daniel showed is quite easy to do with the vector potential, is to add this sort of artificial dissipation in to capture these sort of things. So I think this is okay.
Thanks.
Any other questions? Let's thank our speaker once again.